All right, so if I can get your attention up here. Hey, chapter 8, all we did was exponential growth and decay to begin with. Okay, the first, if we think back to 8-1 through 8-3, okay, 8-1 through 8-3 was exponential growth and decay. Okay, and dealing with graphs. All right, so when you're looking at your practice test for chapter 8, this is really dealing with problems 1 and 2, as well as the very back page, 21 through 22. Okay, that's all exponential growth and decay. You're dealing with the graphs and the story problems. Remember, that's the form y equals a b to the x. What's a? Good, that's our starting point. More commonly referred to as our initial value. Okay? If you want to stay in class, you need to focus. Either work on your work or pay attention. Otherwise, you got to head out, and I got some other stuff you could be working on. B. Yeah, it's our rate of change. Okay. When you recall our rate of change, if our B term was greater than 1, that was growth. If the B term was greater than 0, but less than 1, so that's the math-ese, if you want to think of it that way, that was decay. The more common way to think of that is it's between. B is between. Having a hard time with spelling today. Between 1 and, or 0 and 1. Okay. All right. So that was our formula there. X was the number of times, number of repetitions, if you want to think of it that way. Number of repetitions, or the number of times you increase something, or the number of times something compounded. Okay. And Y was your ending value. All right. So when we were graphing it, when we graphed that, remember we always started with determining where our initial value was. Okay? So when we were building our tables in our graphs, we always determined what our y-intercept would be. Okay, that would mean when I'm actually graphing, if I just do a quick generic graph, let's say of a growth function. Okay, our y-intercept's right there. We'd figure that out, and then we'd find a couple points on each side, enough that we would see that curve. Okay, y-intercept was always when x equaled. It was always when x equaled 0, and the other way to think about it, it was our initial value. This point up here is always our y-intercept. Because when we put 0 in for x, b disappears. It becomes 1. Okay? So that was 8, 1, 2, and 3. That's really what we did there. We had some story problems we had to put in this form. We had to figure how many times something repeated itself, or usually like the number of years, okay, or the number of times. We talked about doubling. Doubling means it has a rate of 2. Tripling would mean a rate of 3. Quadrupling, 4. Okay. Oh, thanks. I don't know if I need it. But yeah, you just said it there. That's fine. Okay. Good. Any questions on that? Okay? 8.4 through 8.8 was the second part of the chapter. Okay? And we had properties of exponents, and within there we sprinkled in those scientific notations. So, few properties of exponents. I'm going to just use A as, or maybe I'll use B as my base, since that's what we've called base of them. So if I have B to the power of 1, anything to the first power is? It's itself. It's not 0. Okay? Anything to the first power is itself. Anything to the 0 power is 1. If I had B to a negative power, let's just use a random letter like negative n. What do I do if there's a negative exponent? Well, I have to think of it as a fraction, so I put it over 1 if it's not already in fraction form, and then I would move it to the other side of the fraction bar. So it would look like that. Or if it began on the bottom as a negative, so if it was already 1 over b to the negative n, in that case I would move it up. And that would become b to the n. And so those are the first properties we dealt with. That was more 8.4. Okay? Any questions there? Okay, then we talked about b to the n times b to the, I don't know, give me another letter. K. If I'm multiplying powers with the same base, what do I do to the exponents? You add them. You add those up. So that's the math behind it. If you want to put if you want to give yourself an example, you could say like b to the third times b to the second is b to the fifth. You would add them up. It's the 3 plus 2. Okay. And if you have b to the n all to the power of k, like that, that's called a power to a power. In that case, you have b to the n times k. You multiply if you have that parenthesis there.
So you always multiply, not?
No. You always multiply if there's parenthesis. Yeah. Brina.
So if you were, if you were to replace that b with like 3.
Okay, so b to the third.
Or no, just have, because on the quiz I got confused and said 3b to nk or something like that.
Okay, so let's give, alright, so 3, like that,
Yeah.
and then put a letter after it, b,
And then it had, k.
okay, like any power,
Yeah.
okay, so to the second.
So would you distribute that to the 3 and the b, or just?
That would be distributed to just the b, because there's no parentheses.
Okay, and then if it was, you would distribute it to both?
Correct.
Okay.
Yep. And so let's do one like that here in a minute. Let me give you an example of this one. So if I had b to the third all to the fourth, that would be to the b to the 3 times 4, or b to the 12th. Okay? So what you're talking about is if you have, let's give a different example. If you had, say, let's use yours. So if we had 3b to the 4th, that's as simplified as you can do it. Okay? So that would be your answer there. That's already in simplest form. However, if you had a different example, and say you had 3b to the 4th, like that, that means you've got to bring it into each part. That's 3 to the 4th times b to the 4th. Okay? And so that would be your 81 b to the 4th. Make sure you don't put 12 there. It's 3 times 3 times 3 times 3, or 81. Okay? How many are with me? All right. Any questions? Okay, so we have all of these properties so far. Here, I'm going to separate them and kind of zoom out here. So hopefully we have those down. We have one more property. Okay, and that one was, move it over here, where I had, say, b to the n over b to the k. When you're dividing, it's the same as subtracting, b to the n minus k. So an example of that would be, say, b to the third over b to the seventh. That would be b to the 3 minus 7, or b to the negative 4. And we can't leave it as a negative exponent, right? To make it positive. Peter?
Why do you bring it down?
Yep, you bring it down. So that part would drop down. We call it 1 over b to the 4th. Make it a positive. Okay, so we don't want our exponents ever to be negative. Okay? I think I've got all the properties. I better double check over there. I guess I never showed an example of one kind of in the same mold. If you want to put an example that looks like this, you have 2 to the, or rather than 2, let's use a letter. A to the second and b to the third, all to the 4th power. You got to distribute that into each part here. That becomes a to the 4 times 2, or 2 times 4. And b to the 3 times 4. Okay, so a to the 8th, b to the 12th. All right. Only thing we haven't covered, does anyone know what it is? It's one thing we worked on this chapter. It was actually in 8-5. It kind of went along with all those things. Scientific notation. Scientific notation. So, recall scientific notation. When you're in scientific notation, you have some number times 10 to some power. Okay? This number right here, whatever this number is, must be greater than, or must be 1 or greater but less than 10. Okay, so like in between 1 and 9.9999999, and it's okay for it to be negative. So technically it could be between -1 and -9.99999, and +1 and +9.99999. We say the absolute value of that number has to be between this. But that's getting a little too mathese for what we're dealing with. So just think, has to be between 1 and 9.999. If there's a negative sign in front of it, you're okay. All right? So, times 10 to some power. So, for example, if we had 3.25 times 10 to the third, that is a good number. It's in scientific notation. We're okay there. All right? If we had 36.4 times 10 to the fifth, we're not in scientific notation. We've got to move this decimal 1 unit this way. So to make that 36 into a 3.64, and since this front number got smaller, the power has to get bigger. Or another example would be if you had, say, 0.025 times 10 to the negative third. Okay, we got to move this 1, 2 places. So our number there, did it get bigger or smaller? Got bigger by 2, so this has to get smaller by 2. Now when you get smaller, are you moving towards 0 or away from 0 in terms of negatives? You're getting further from 0, right? So I'd have to subtract 2 from that. So it'd be negative 3 minus 2. So if you struggle with those negatives, which some of you did, write it out like that to begin with and then do the math. Negative 3 minus 2 is negative 5. Okay, you know where your strengths and weaknesses are. Okay, 2 other real quick examples we had. If you had a problem that looked, say, like this, where 4.2 times 10 to the third all squared, you bring that into each part. So you get 4.2 squared. I have no idea what that is. Times 10 to the 3 times 2. We got 4.2 squared. 17.6. 4 times 10 to the 6th. And then we've got to move that decimal 1, so it got smaller. So that's going to get bigger. Oops, it's going to get bigger. Okay? And then we added division 1. So we kind of applied all of our other properties to it. Say if we had like 2.0 times 10 to the third over, I don't know, 5.0 times 10 to the second. Actually, let's not use second. Let's use fifth. Okay, we divide these two numbers. So that's 2 divided by 5, which is 0.4. And then 10 to the third divided by 10 to the fifth. Well, since those are the same base, it's just 10 to the 3 minus 5. So treat it like 2 different problems. And then put it together at the end. You get 10 to the negative second. And then that's not scientific notation. We move that over 1. So we get 4.0. That got bigger, so this gets smaller. So subtract 1. 4.0 times 10 to the negative third. Okay, that's a lot, man. But that's what we just did. That was our chapter. And I didn't go everything in scientific notation. I did the majority of it. But I think we're about done. That's a lot of math. Yeah. Do number 16. Practice test? Sure. Oh, one like number 16? Yeah, let me actually do number 16. There we go. That'll be a good example. So let's look at that. I guess we didn't do one like that. These are time signs. They look like X's. When you're dealing with scientific notation, that's times. So in this type of problem, you multiply the common pieces. The whole number is 42. So do 6 times 7. And then we're going to take our bases, times 10 to the 8 plus 9. Or 42 times 10 to the 17. We're not in scientific notation, so we're going to take that decimal and move it over 1 to make that in between 1 and 10 to make 4.2. Since that got smaller, this one's going to get bigger by 1. So our answer is 4.2 times 10 to the 18th. Okay? Good question. Any other questions? Think we're better? Okay, the answers are hanging up here, so be asking questions during class.